Hi, welcome everyone. My name is Christian Taylor-Wolski and I'm the Space Industry Lead at Stone & Chalk in Adelaide. Many of you know Stone & Chalk Group as Australia's home for emerging technology with hubs in Sydney, Melbourne and Adelaide, serving 850 residents with knowledge, access to capital, infrastructure and guidance. We drive emerging tech innovation for positive impact. Stone & Chalk Space is based at Lot 14 in Adelaide, the land of the Kaurna people, and we acknowledge their elders, past and present, as we acknowledge and respect all traditional owners of land everywhere. We're proud to have almost 300 signups for this event from all over Australia. I'd like to thank our partners for this event about space exploration, the Andy Thomas Centre for Space Resources at the University of Adelaide, and Microsoft. Just a bit of virtual housekeeping. This session is scheduled for 1 hour sharp, the majority of which is dedicated to Director Elachi's presentation and Q&A. You can post your questions in the Q&A tab on the Zoom platform. We've also already had a lot of questions submitted at registration, which we will refer to in the Q&A. I'm now handing over to Professor John Colton, Associate Professor at University of Adelaide and Director of the Andy Thomas Centre for Space Resources. John will be introducing us to this session and our main speaker, Dr. Charles Elachi.
All right, thanks, Christian. As Christian said, my name is John Colton. I'm the director of the Andy Thomas Center for Space Resources at the University of Adelaide, and I'm extremely pleased to introduce tonight's guest, Professor Charles Elachi. Professor Elachi received a Bachelor of Science in Physics from the University of Grenoble, France, and his engineering diploma from the Polytechnic Institute, Grenoble, where he graduated first in his class. Later, he earned a Master of Science there as well, before receiving his PhD degree in electrical science from the California Institute of Technology in Pasadena. As a lifelong learner, he later received an MBA from the University of Southern California and a Master of Science degree in geology from UCLA. Following his PhD, he continued at Caltech, ultimately becoming the Jet Propulsion Lab Director from 2001 to 2016, while also serving as the Vice President of the California Institute of Technology, where he remains a professor of electrical engineering and planetary science. Professor Elachi was principal investigator on numerous research and development studies and flight projects sponsored by the National Aeronautics and Space Administration, such as principal investigator for the Shuttle Imaging Radar Series, co-investigator on the Magellan Imaging Radar, team leader of the Cassini-Titan radar experiment, co-investigator on the Rosetta Comet Nucleus Sounder experiment, among many, many others. He is the author of over 230 publications in the fields of space and planetary exploration and has authored 3 textbooks in the field of remote sensing. As you might expect, Professor Elachi has received numerous awards, including the NASA Exceptional Scientific Medal, the NASA Distinguished Service Medal, 2 times the NASA Outstanding Leadership Medal, and the Wernher von Braun Award, again, among many others. Of note, in 1989, asteroid 1982 SU was renamed 4116 Elachi in recognition of his contribution to planetary exploration. Professor Elachi is now also an adjunct professor with the University of Adelaide and attached to the Andy Thomas Center for Space Resources. And with that, it's my great pleasure to welcome Charles to the podium.
Thank you very much. First, let me start by telling you how delighted I am to be in Australia. It's one of my favorite countries. I've been here dozens of times, and now Adelaide is becoming one of my favorite cities. This is my first trip here, but it's always like everywhere in Australia. People are so friendly, beautiful countryside, and of course here some great wine that you have around Adelaide. So what I'm going to basically tell you is about the advances which have happened in space exploration in the recent past and where we are heading, in the future. And I want to start by saying that Australia plays a significant role in our exploration, starting with the Deep Space Network, which is just outside of Canberra. That's basically one of the stations which allow us to communicate with our spacecraft. We have a number of scientists which have been trained in Australia, or they are collaborating with us, who are working at JPL. And of course, there is Andy Thomas, who was trained in Australia, grew up here, graduated from Adelaide, worked at JPL. He and I were very good colleagues, and then he became an astronaut on doing that. So Australia plays a significant role in our space exploration. So first, let me start by talking about why do we explore. So if you look at this picture, it covers a part of the sky which is about the size of a dime that you put at the end of your arm. So this is a little teeny part, of the sky that you are seeing. And look at how many stars and galaxies you are seeing in that very little teeny part. And if you look at the whole sky, there are literally billions and billions of stars and galaxies. And if you zoom on some of these galaxies, you can see that they are formed of many stars. So when you see a galaxy, it's literally billions of stars which compose that galaxy. And if you zoom on one of those stars, which we call sun, we actually see planets around it. And this is our solar system. Going from the left, you have Mercury. The Earth is the third planet to your right, and then going to Jupiter, Saturn, Uranus, and Neptune. And these up to scale relative to each other. And what we're finding in the last decade is that every star we look at, we actually find planets around it. So we're talking, considering how many stars there are literally thousands, if not millions, of planets just in our galaxy. And when you look at the whole universe, you have even more. And if you zoom on one of these, is what we see on the left, that our planet, what we call the blue dot, and that's a planet which had the right temperature, the right ingredient, the right chemistry, which led to life like you and I today. I mean, we started from the Big Bang, which were particles which were formed, and through evolution, we led to life on this planet. And one of our goals is to see, is there life on other planets, and are there planets similar to ours? So the first one we have been focusing on is Mars. That's the planet you see on your right. These are to scale. So Mars is about 1/4 the size of Earth, but Mars has atmosphere, not exactly like Earth, but much thinner atmosphere. It has polar caps, as you see at the bottom, which are made of H2O, water, and carbon dioxide. And the geology looks very similar to what we see on our planet. Matter of fact, this is an example of one of these pictures is the Grand Canyon on Earth, and one of the pictures is the Grand Canyon on Mars. I let you guess for a second which one is which. That's a test usually I give to my students at Caltech. Well, now that you guess, the one to the left is Earth, and the one to the right is Mars, and the size of that canyon is about the size from across Australia, on Mars. So it's a huge canyon that you see in there. Another test I give to my student is, guess which one? One of these pictures was taken in Western California, or Central California, sorry, and the other picture was taken on Mars with one of our rover. Again, I do a test, and I ask my students, and I ask, and I have audience directly, how many of you would think the one to the left is Earth? And usually I get 50% of the people who raise their hand, and then I ask people, which one is the one to Mars? Do you think the one on the left is Mars? And 50% of the people raise their hand. I have to tell you, I forgot which one is which. But the point I'm trying to make is when you look at the geology on both planets, it's very, very similar. The only reason I know that the one on your right is Earth is if you were very careful at the beginning of it, actually there was a snake which was snaking around. So that tells me that the one is Earth. Matter of fact, let me go back. You see the snake to your right? It's black and white, between the rocks. It's on the right edge, just about halfway through the land picture. And you can see it here kind of moving. So that's how I know that the one to the right is actually Earth. But again, the point I want to make is that the geology is very similar. The evolution of the geology has been very similar. So the key question is, and we know that in the early days there was water on Mars because we see dry riverbed, we see dry lakes. And the key question is, could have life evolved on that planet in the early days when Earth, also life evolved on Earth? And for some reason on Mars, actually the water froze, went below the surface. And the question, are there any signatures of life? And if we can find it, is it similar to life on Earth or is it different? So now we have been, not many people realize, literally for 18 years or 16 years, we had continuous presence on the surface of Mars. We have had rovers which are roving around Mars of different sizes, exploring that planet. So you can see on the picture on the left, the little teeny rover, that's Pathfinder. That's a rover we launched in the late 90s. And we were just learning how actually you drive on Mars. Because one thing, for your information, it takes about 10 to 20 minutes for the signal to go from Earth to Mars, 10 to 20 minutes for signal to come from Mars to Earth. So we cannot really joystick. It's not like the toys that you have. So the rover has to be fairly autonomous and had to have enough intelligence that actually it can do function and avoid hazards. Behind it is a model of Spirit and Opportunity. So that's about the size of your desk. And the one to the right is Curiosity. That's about the size of a car. The one to the complete right is that actually a self-portrait of Perseverance, which is the rover which is actually on Mars. So this is not a fake image. This is actually a selfie taken by the rover actually on the surface of Mars. And the challenge with these rovers is actually they have the equivalent of a chemistry lab at a university like University of Adelaide, and all compacted to be in that rover. So it includes the oven where we can take sample, put them in the oven and heat them, see what gas is being emitted. It has X-ray spectrometer, it has gamma ray spectrometer, it has a laser beam which can zap the rocks and actually evaporate material from the surface so we can analyze it to do that. So it's very much like chemistry labs. The X-ray is very much like when you go to your dentist and they take X-ray of your teeth, except a lot more expensive, here. And that will allow us to understand the composition of the chemicals that we have on the surface of Mars. So let me give you an idea about the challenge to get to Mars. After we travel about 225 million kilometers, we have to arrive to Mars within a circle of 2 kilometers. So we're coming at the right angle to the right place. So let me give you an idea what that means, 2 kilometers relative to 225 million kilometers. That's the same if I go outside my office in Pasadena, California, and hit a golf ball toward a golf field in Australia, and the golf ball has to go straight in the cup. That's how challenging it is to navigate. And to make it a little bit more interesting for the really good golfers, is that cup is moving. So you have to still land on it, and it's moving at about 60,000 miles per hour. So you really have to do some very accurate navigation to do that. And part of that navigation is using the deep space antennas. One of them, or a station that we have here in Australia, played a significant role in that capability. The other challenge is the speed at which we are coming and the mass of the spacecraft at which we are coming. The energy, the total energy, is the equivalent of 18,000 race cars going at full speed. And we have only 5 minutes from the top of the atmosphere to the bottom of the atmosphere to dissipate that energy so we can land very softly, on the surface. So we use a series of techniques, and you will be seeing that shortly in a video, where actually we use a heat shield, and that heat shield actually absorbs about 90% of the energy. It works the same way as if you are driving at high speed and you stick your hand out of the window, you feel the pressure of the air on your hand. Same thing on Mars, we feel the pressure which is happening from the atmosphere, except the atmosphere is not thick enough to completely slow us down. So after that, we have to drop the heat shield and open a parachute, supersonic parachute, the biggest parachute ever built, and that will slow us even more, and that even is not enough to slow us completely so we can land softly. So then we use retro rockets, which have to slow us down even further, and then we hover above the surface at about 10 meters above the surface, and then we sky crane the rover very slowly so it actually touches the surface, very softly. And this is a picture of the actual rover. That's the rover which is now on Mars. We launched about a year ago, or a year and 2 months ago. And that's during the assembly. And as you can see, the rover is about the size of a car. It's all run by electricity, electrical power. The electricity is generated by a small nuclear reactor, or what we call an RTG, for radioisotope thermonuclear system, where we use plutonium, which as it decays, it generates heat, and then we use thermocouples to use that heat to generate electricity. The whole rover runs on about 140 watts. Now we accumulate energy in the batteries and then we use it to actually drive. But again, we had to develop a lot of technologies, very low power, very efficient, very lightweight kind of electronics, so we can, and motors, so we can run it with that little power that we actually have. You see all the people wearing what we call bunny suit, and that's because we want to make sure the rover is very clean and make sure that there are no bugs that we take with us from Earth, to Mars. So we really have to have the rover very cleaned up. We use chemical cleaning, we use thermal cleaning to assure that we take a minimum amount, of bugs from Earth to Mars. And that kind of give you an idea of how we package that rover. So the rover, you see it, where it says rover, and basically it's folded so we can fit within the capsule. Behind this is what we call the descent module. That's a retro rocket which are going to hover and allow us to sky crane the rover. Both of them are put inside the back shell and the heat shield. The parachute is at the back of the heat shield. And then we have what we call the cruise stage or carrier. That's what takes the whole package to Mars and then drop it into the atmosphere, of Mars. And we have all kinds of cameras all over the place. So you are going to be seeing picture of looking backward as the parachute open, looking forward as the descent module goes down, and then after looking at the descent stage as it separates after we do the sky craning, and then the rover landing on Mars. And this shows you what we call the high bay at JPL, where we're actually assembling, that whole package. So that was about a year and a half ago. And you can see the rover in the middle of the picture, the descent module farther down, and the cruise module to the right. So now what I'm going to do, I'm going to take you to the mission operation room at JPL. When you are director for 16 years, they named the Mission Operation Control Center after me, which is really a great honor. And you are going to see actually what we were seeing in real time when people were sitting in the mission operation room.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for
So this is being played in effectively real time. Now the data is delayed by about 10 minutes of coming to Earth. So here you see the camera looking up, which deploying the parachute, behind it. Of course, that was a big relief when we knew that the parachute had actually opened, properly, because that was one of the big risks that we kind of were worried about. Then now you see the heat shield being dropped, and you see Mars behind you. So that's exactly it's all in real. So if you were sitting on that spacecraft or that rover, that's what you will see in the background. You see the heat shield going farther down, and we had to maneuver to get away from it so we don't actually hit the heat shield. Yeah, I think it looks like it froze, in here. So, here we go. So actually you will be seeing things moving because one, the lander is sitting under the parachute, so you are oscillating back and forth. But also we want to land at a very specific spot. So we have an image in the lander which tells it which is the spot we want to land at. And the camera, we're basically comparing the images. It's like when you do face recognition. So the camera is comparing what we are seeing to where we want to land and moving the lander to go to that area, so we have a very accurate, landing in there.
4.2 kilometers. We have confirmation that the lander vision system has produced a valid solution.
And you see one of the people who are working on this mission is giving a regular report about what actually is happening. And by the way, when we were landing and these images were coming down, they were distributed worldwide in real time. So that adds a little bit to the tension, in there, because, everybody, your mother and your friend and your cousin, they are all watching what's happening at that time.
We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about 1 kilometer off the surface of Mars.
TRN Safety Bravo.
And as you start seeing more detail, it looked very much like Central Australia. You know, it's a very dry area, but also you can see signature of riverbed, sand dunes, which are basically surfaces because of the wind on Mars. And you can see erosion. For people who are geologists, they can see erosion, which look very much like water has eroded those areas. So now we are getting closer to the surface. And in a second, you see the plume of the retro rocket, which are firing. You can see them blowing up the sand from the surface. And then the camera will actually show you the descent module separating, that's the upper picture, and the rover below it actually being dangled, you know, on the rope, you know, sky crane. And as soon as it touches the surface, we cut that rope, and the descent module actually flies away, and the rover is on the surface. And just imagine all of this is happening on another planet, and we are getting it in real time. And you can see the excitement of the people, you know, when all the landing worked perfectly well. So now the first thing we do when we land is we immediately take pictures of the location to make sure that we landed all safely. So this is the first picture which taken from a camera just below the rover. And you can see the right, the shadow of one of the wheel, and to the left, the shadow of the box, which is the rover box. And then shortly after that, we start testing the different system. So here we are testing the wheels that actually we can actuate them right and left. And we take our time to do that because we have basically a very valuable asset, and we want to make sure everything is working fine. And this shows you the testing that we are doing for the arm that we actually use to collect sample, which I'll describe to you in a minute. It's an arm very much like your own arm. It has the same dexterity and the same flexibility of your arm. So the purpose of this mission relative to the previous one is we want to collect samples. So the rover will be driving around. It has a number of instruments which will analyze the composition of the rocks, including one of the instruments. The principal investigator is Australian. She is working at JPL. And then basically we collect those samples. It's about the size of a pencil. And we are going to collect about 31 samples and put them in that sample container or caching sample. And so far in the first year, we have been there for about a year, we have collected about 14 samples. And over the next year, we'll collect to get about 31 samples. And then the intent is this sample will be put on one location, you know, or cached at one location. We'll be sending another mission, which will land on the surface of Mars with a retro rocket. A small rover will go out, grab that container, put it in the nose of the rocket, launch it in orbit, and then there will be a spacecraft which will rendezvous, you know, with that container, grab it and bring it back to Earth, and then it will be distributed for a number of places around the world. I wouldn't be surprised if there will be Australian scientists involved to do the detailed analysis, you know, of this sample. And this mission is being done jointly with between NASA and the European Space Agency, and there will be a number of international scientists involved with it to analyze those samples. Now, one thing which kind of we added to this mission, we added a helicopter. Now, people will say, well, what's a big deal? You know, my son or my cousin have a drone. The difference is on Mars, as I told you earlier, the atmosphere is very thin, and it's the equivalent as if you are flying at 90,000 feet. We have never had a helicopter flying at that altitude. So we had to develop a capability where the whole helicopter is about 1.5 kilograms. All the cameras, the power, the intelligence on it, the communication link, and we had to make sure that we have enough intelligence that when the helicopter comes to land in an area, to make sure we are not landing on a rock and will tip the helicopter. And these rotors have to spin at many thousand rotations per minute to be able to do that. And here you see it, you know, being assembled, the actual flight camera on your right. And on the left, we had to do testing in our vacuum chamber where we actually simulated the environment on Mars. And of course, like many of these exploration things, they don't work perfectly the first time. You know, we see problem, but always we come back and we try to understand what the problem, and then we perfected them. So I'm going to show you now actually one of the first flights. You see the helicopter is at the bottom left, actually on Mars. The picture is, or the video is being taken from the rover. And that was the first. So this is the first time we're actually flying on another planet. So that humanity actually developed helicopters similar to the Wright brother 112 years ago, where they actually did the first flight ever. And at that time, it was a curiosity. And look at what happened over 100 years. Now we have airplane, you don't even think twice about going and flying on airplane. The same thing now on Mars. This is the first time ever that we have flown on another planet. And we are starting to think about building bigger helicopters and more capable helicopter. And I can envision, by the way, the helicopter is coming back. We originally planned to do 5 flights. We are on flight number 26. And now these helicopters are basically going ahead of the rover, surveying, the surface of Mars, so to guide the helicopter to drive around and go and explore the different areas. Now, this is about what we're doing on Mars. So I can envision in the future when we send astronauts to Mars, they will have helicopters, they will have rover, which will help them extend their capability over many tens of kilometers to many hundreds of kilometers. Now, this is not the only thing we're exploring, to look for potential life in our solar system. Jupiter is another place. We have a spacecraft called Juno now, which is taking pictures and trying to understand the dynamic in the atmosphere of Jupiter. And this gives you an example of some of the images. Just to give you an idea, that white spot at the top, that's a big hurricane. That's the size of Earth. So you can put all of Earth in that hurricane. And what we're looking at is to be able to understand the dynamic of how these hurricanes evolve, and that will shed light about hurricanes here on Earth. And one of the particularly exciting that's another picture of Jupiter taken from the Hubble telescope. And one of the satellites of Jupiter called Europa is one of the particularly interesting satellites. It's about the size of our moon. It's made of ice, H2O ice. We see this brown feature on it. They are organic material, and we see the fracturing which has happened. And based on a number of observations, we believe there is actually a liquid ocean of water just below the surface. We have roughly an idea about how thick that ice. So in order to quantify that thickness of the ice, we're actually sending a mission which is called the Clipper. It's being assembled as we speak at JPL. It will be launched in 2024. And then that satellite actually have a radar sounder which will allow us to measure the thickness of the ice on Europa, because in the future we want to be able to put a lander, drill our way through the ice, and actually put a submarine in that ocean to see could there be life in that ocean, because it's made of H2O, it has organic material, it's liquid like our ocean. And when you go deep in our ocean to the bottom of the ocean, actually we see life around the vents in the ocean. It's not light, but it's energy. So the combination of energy, organic material, and water, which have led to life at the bottom of the ocean. And one of the objectives of exploration is to see if there is life in that ocean today. And the same thing around Saturn. We had a mission which just finished, called Cassini about 2 years ago. And there is a satellite around Saturn which is called Enceladus, which also is very similar, to what we are seeing on Europa. And to move to the human program, one of the major programs that Australia is part, of that program is called Artemis. So that's a program to get back humans, to Mars and to stay there, and basically capitalize on the resources on Mars, both scientific as well as potential commercial. And one of the key things that University of Adelaide, working with industry, in Australia, is the objective is, as part of the Artemis program, to develop a rover which can be carried, to the moon, and that will be a significant role or major role that Australia is playing in our exploration of the moon. And here, let me kind of answer one of the questions that I got ahead of time, is the role of the commercial sector. Well, the commercial sector is going to be playing a major role in future exploration. Now that the technology has been developed for transportation, both to Earth's orbit as well as to the moon, and with advances in electronics, I think there are a number, of companies that are basically developing spacecraft. Stone and Chalk is one of these companies, where they are developing capability to be able to put spacecraft both in Earth's orbit as well as on the moon, and develop the commercial capability to that. And Australia is playing a major role in that capability. So for the young people who are interested in being in space, Australia is playing a significant role to make that happen. Now let me talk about coming to our own planet, what we are doing. Yes, we are exploring space, and there are lots of benefits that I can talk about a little bit later. But also we're looking at our own planet and monitoring what's happening on our environment. And we have 4 major foci that looking at our planet. One is to understand better what's happening in the ocean, is about the ocean rise. Another one is to look at the carbon dioxide being emitted and being in our atmosphere, which leading to warming. A third one is to look at the water resources. In many places, I can speak for California, we're having a lot of water shortage happening because of the global warming and global change. And then to look to be able to monitor and possibly predict extreme event, either human-made or natural-made, like earthquake, floods, hurricane. So let me give you just a flavor of the kind of experiment that we are doing. One is about the ocean rise. We have been monitoring the ocean for literally the last 30 years on a joint program with the French Space Agency. And the ocean is rising, as you see at the bottom right. Actually, it has been continuing rising. And the reason the ocean is rising, there are 2 factors. One, as the temperature on the surface increases, that expands the water, like what happened in any object with heat, it expands. And that accounts for about half of the ocean rise. And the other half is coming because the ice is melting. Because of the warming, the ice is melting in Greenland and Antarctica. And we have been monitoring that for just over 5 years, as you can see at the top right. Even that the amount of ice is going up and down, but on the average, it's going down. And if you can see the scale there, we're talking of hundreds of gigatons of ice melting per year. And that contributes to the second half of the ocean. So no question, global warming is having a major impact and leading to ocean rise. And if that continues in 30, 40 years, a lot of the coastal region will be flooded, and that will be of major economic impact and human impact. So now we have the capability of monitoring from space almost every environmental parameter on our planet, be it the amount of carbon dioxide, amount of ozone, temperature, ocean wind. And here I want to tell you, if you go and Google Eyes on Earth, that's a program that we have developed at JPL, which will allow you to see almost in real time any of the environmental parameters that are being acquired from our satellite. So remember, Eyes on Earth, if you Google that, you can get that app and you can see it on your iPhone. So you can go and impress your friends of telling, okay, which parameter on our planet you want to see from the last 24 hours, and that's what you will be able to access. And shortly, we have a mission that we are doing jointly with India that will be launching. It's called NYSAR. And what that mission will allow you to do, it will allow to map every week the changes which are happening on our planet down to a centimeter. And to kind of give you a flavor what that means, okay, so this is monitoring from an experiment that we are doing, the Los Angeles Basin. And here you are seeing the Los Angeles Basin over the years moving up and down few centimeters. And that's happening because when we pump water and pump oil, the surface subsides a little bit. And then when the snow melts in the Sierra and feeds the water table, it moves up a little bit. So that allows us to see actually the Earth breathing. And imagine we're going to be doing that all over the world. So that will allow us to monitor water table, particularly in very arid region where water is being pumped. And that could have major impact for the future availability of water. That's being used commonly now in the Central Valley in California. And also it will allow us to see the motion which is happening along the faults and the tectonic. And that will allow us to determine area where there is high risk, of potential earthquake. It will allow us to see the surface change on volcanoes. So it will allow us to determine potential eruption which are happening. So this is an example of the kind of thing that you are going to be seeing in the future, which allow us to monitor all the potential hazards, both, as I said, man-made as well as natural. And then the other thing which is advanced, and that's particularly relevant to places like Australia, with the advances of electronics, we can build spacecraft basically the size of, of a little table. So this spacecraft, which we call Raincube, it's monitoring the rain. And I could have brought it in my luggage when I came from the United States to Australia. Now, I'm sure the people at the border would have been wondering what in the heck is he bringing here. But that gives you an idea about the size of spacecraft which are capable of significant amount of monitoring, which are being developed, today. And this is an example of this spacecraft actually showing you the profile of the rain. And these spacecraft can be developed at universities, at startup companies, everywhere and around the world. And Australia could play and is playing a major role in making these things actually happen, which will contribute to the overall capability in space exploration as well as space monitoring. And this is another example, another spacecraft similar to the one I just mentioned to you, which show profile of precipitation in the atmosphere as well as image across the surface of precipitation. And this mission or this capability we are going to be using to monitor tropical storms in the Pacific and be able to predict, the high energy storms which could create a lot of damage in the tropical, region by monitoring the precipitation in the tropical region across the Pacific. And this is going back to this, what I mentioned to you, the eyes on the Earth. Not only you'll be able to see on your iPhone the different parameters, but also you can see it going in time. You can go backward. You can say, well, let me see the carbon dioxide over the last year where it has been emitted. It will allow you to do that. And when you click on the different spacecraft, because it will show you where the spacecraft is, it actually will give you the parameter or the capability of that spacecraft. So this is a capability which you are going to have on your iPhone in the future, and as today as well as in the future, about monitoring our planet. And this takes me for my last slide, because I like to show it with a quote from Teddy Roosevelt, which says, "Dare mighty things." The whole quote is roughly it's far better to dare mighty things than to sit in the twilight that knows neither victory nor defeat. So that to show you, when you are doing exploration, it's always challenging. But you want to lean forward and do really mighty things. And that's the kind of thing that places like Australia, university, and companies in Australia are actually doing now, even though there is a risk of failure. Not all of them are going to work. But like anywhere in exploration, you actually will be able to advance by taking these kind of risks. So hopefully you enjoyed this. And I think what I'm going to do now is to answer some of the questions that I have received so far. And then if we have time, then we can take some questions from the audience. So let me address first a number of student questions, that I got. And again, I'm not going to go one at a time, but I will give you an idea. So there was a question about what kind of engineering you need to study, or the student need to study to be able to be part of exploration or space program. I can tell you any engineering discipline is important, for space exploration. At JPL, we have chemical engineers, electrical engineers, aerospace engineers, material science, biologists. Almost every engineering and scientific discipline is needed to do the space exploration. The other question is about, for the role that Australia is playing and what high school students can do to be part of the Australia future in space. The space sector in Australia is expanding. You have the Australian Space Agency, but also in addition, there have been a long history in Australia in radio astronomy, in the telecommunication, using antennas to communicate with our spacecraft. So effectively, Australia is playing a larger and larger role in space exploration. A perfect example is the Artemis program that Australia signed to be partner with NASA on it, as well as a number of other countries. And another example is what University of Adelaide is doing on developing a small rover that could be potentially taken to the moon and actually operate that on the moon. The other question is about how can people from the international background be part of space exploration. As I mentioned, many countries actually are developing capability in Western Europe, Japan, Singapore, Australia. So there are lots of opportunities for students to do that. For students to actually work in the space program in the United States, basically one best way to do that is to actually go and get education in the US or to go through the space agencies. So the JPL, we have collaboration with the Australian Space Agency, so people can come through the Australian Space Agency and work at places like JPL. Let me go. Some of these are kind of redundant. Looking specifically at South Australia space ecosystem, as I mentioned, you have actually a number of companies like Stone and Chalk here, and Fleet, and a number of other companies which are involved in space exploration that you can be part, of these capability. One question here is about where do I see the future of spaceborne multi-wavelength synthetic aperture radar for planetary observation. You just saw about the Earth. I showed you an example for it. We actually used radar, for mapping Titan, which is cloud covered. And then we are planning to use radar sounders to basically look at the ice thickness, in the case of Mars. And there are talks in the future of sending orbiters, to Titan, orbiters to Venus. So there are lots of opportunity in that area. And one question also here is about flexible and rollable solar panel. No question, that would be great if we can develop the technology to fold the solar panels and roll them. That will help us because at launch we have either to fold them or to roll them in. An example is the space station, solar panels. Terrestrial analog and facilities, to support future Australia space exploration. A perfect example is at University of Adelaide, where they have a facility and developing a facility both here as well as in agricultural center outside of Adelaide, to actually simulate and use those as what we call lunar yard or Mars yard to simulate that capability. Challenges of material development for space application. Yeah, that is always a challenge because the environment in space, you have not only radiation, but also you have the change in temperature. So you need material which can sustain that change of very low temperature and very warm temperature, like in the case of Venus, and material which can sustain, or electronics, we can sustain the radiation environment. How can Australia contribute in the area of life science and across the board in space and life sciences? Just before I came here, we met with psychiatrists and cognitive scientists, and they were doing research on how can astronaut adapt for long-term travel, long stay at another planet. So as I mentioned earlier, you need people from every discipline to actually be involved to make a successful space application. One example here was talking more about specific, where it says, should we focus on more than Mars and elsewhere when taking our first giant leap into cosmos? Yeah, I mean, you go first to the nearest planet, and that is the moon. Then you go to the next planet, which is Mars, and then you continue your travel across the solar system. During crashing of any lander, what calculation goes wrong and how to rectify it in order to stop its crashing? When you are landing on another planet, you don't have the time to stop it. You have 5 minutes, and your time delay is about 10 minutes. So by the time you get your first signal saying we are at the top of the atmosphere, things have happened. Either we have crashed or we have landed. So to avoid these problems, we actually do a lot of testing. So before we send these spacecraft, we test them a lot, and not only test them within the range that we expect, but we test them all the way to breaking them. So we know how far are we from being at the edge of the cliff. So a lot of testing, a lot of smart people who work on these things, because you really don't have the time to actually react, particularly when you are doing that. What keeps you going at your lowest moments? I can tell you, I don't remember any day where I didn't look forward to go and work at JPL when both I was a researcher and then I was director. because I know every day we're going to learn something. And I always tell the employees at JPL that, look, we are in the business of exploration, and every explorer had bad days. There is no explorer which had only good days. So be prepared. If you want to push the limit, there is going to be bad days, but the key thing is not to give up, but to basically learn from these bad days and be able to do the next thing. So we actually did have a crash of a lander in the late 90s. Of course, we were very disappointed that that happened, but we learned from it, and for the last 16 years or 20 years, we had successful mission from that based on learning from that experience. Other people could have given up, but when you are really an explorer, you never give up. You learn from the error and the mistakes, and then you keep pushing the limit. And the same thing, my advice for the companies in Australia. Yeah, there will be some setbacks on doing that, but if you really want to explore and participate in the business of exploration, you need to be prepared, to keep going, even when you have setbacks. What have been biggest challenge in success in management? Always be an optimist. I always believe in the humanities and the talent of the people that are working in this area, and there is talent across the world. I've encountered a lot of great talent here in Australia. As I said earlier, we have a number of Australians working at JPL that helped us in the success, and I have seen the successes that are happening here in Australia. So it's really, you have to be always an optimist and have confidence that you can overcome any setback. That's a critical element, not only in space, but in everything you do, be it if you are a musician, if you are an artist, if you are an architect. You look at the really big challenging things as opportunities for you actually to learn and overcome these things. So I think I addressed almost the majority of the question that I received ahead of time, and I see John has a few additional questions here.
And that's absolutely right. So one question we received is, okay, spirit. You talked about spirit and opportunity and curiosity and perseverance. You alluded to some other missions that are also on the horizon. What's the next big thing?
Well, the next big, there are a number of next big things. That's what's exciting about this. Clearly getting back to the moon with astronauts and staying as a permanent presence on the moon is a major activity that we're doing. And I'm delighted to see Australia being a partner, with NASA doing that. The other thing in more planetary exploration is for search for life, in other planets and detecting life. And the third one, which I would say these are the three big things, is to look at neighboring stars and see if there are planets similar to our planet, and then to be able to see if there is life on those planets. Now, we don't expect people to be waving at us saying, here we are, but if we can find a planet which have the right temperature, which have water vapor on them, which have methane, which have organic material, that could be an indication that possibly life could have existed, on those planets. So these, I would say, the three in exploration. And clearly monitoring our planet is the fourth part that I would consider very important, because we are doing damage to our planet, with the global warming and global change. And we need to be good custodian of it. And I'm an optimist. I think as a human, we'll be able to figure out a way how to manage these factors on our planet so we can leave a great planet for our children and grandchildren and descendants beyond that.
Fantastic. Well, I actually did receive a question as well. And I think it's a good one that helps, that sums up many of the points that you've made here. And that is, what is the Andy Thomas Center for Space Resources? And what is it specifically that we do there? I'll take just a minute to answer that. But again, it highlights a number of the points that you've raised here. So the title of the center sounds like it's very much focused on science and engineering, and that is true. We are focused on that. But the overriding mission is to support long-term human presence in deep space. And so by necessity, what that means is we need to answer some of those science and engineering challenges and develop the tools that we'll need to support those human beings. But the most critical part of that mission is going to be the humans themselves. So necessarily this involves the entire university. Yeah. All the schools, all the faculties. And so you've been in meetings this week with the our psychologists, our business folks, our plant scientists,
architects, and
the School of Architecture, exactly. We have an artist in residence at the center because artwork and that kind of human expression is going to play a major role in keeping crews healthy and then populations healthy off planet. So we're involved in all of those things. We do have some specialist areas that match up and line up with the University of Adelaide particular areas, and then we have partners at other universities in Australia that help us to build a holistic picture there. But for us, it's space construction, so lunar and Martian surface civil engineering, autonomy, AI, and machine vision from Australian Institute of Machine Learning, and then space agriculture is led by Waite Research Institute and the team out there. Would be three broad areas that encapsulate all of that teamwork for us.
And actually, let me add to that, because there was one question now I remember, which talks about what's the benefit of space other than the gaining the knowledge that we get that. Well, because we are pushing the limit and we're doing some for the first time, we have to invent things. I mean, technology, and invent them. And I always love to give two examples. One example, I'm sure everybody in the audience has an iPhone, and your iPhone has a camera on it. Well, the focal plane of that camera was developed at JPL for our telescopes, for our space telescope, because we needed a focal plane, if you want, which is very lightweight, very low power, and very sensitive. And an entrepreneur thought, wow, I can use that into cameras. And look at all the difference that it made now in all these cameras. The other example is what John mentioned. Even that the Andy Thomas Center is working on deploying Rover on the moon, but they have to develop a lot of capability for robotics. Be able to do robotically, to do construction, to do motion. And all of that capability is going to benefit the mining industry, the construction industry, almost every industry, agriculture here on Earth, by developing this capability of autonomous, be it drones or be it rovers on it. So there is a very direct benefit from these investments, not only for lunar exploration, but also for our day-to-day life.
Well, thank you very much. Charles, that was a fascinating talk. We really appreciate your time. To the students out there, we would love for you to come join us at the University of Adelaide and help support the return of humans to deep space. And with that, I think I thank you again for tonight, and we'll go ahead and sign off for now.
Okay, thank you again at Stone and Chalk for arranging this, and it is a pleasure to be here.